Here we have a single voltage source, Vs, that is supplying two load centers connected in parallel through a transmission line of known impedance. The voltage across the load is measured to be 240 volts, which we will use as a reference phasor. Our task will be to determine the source voltage in this network. We begin our analysis by labeling the various currents and voltages in the circuit as shown. Our approach to determining Vs is straightforward. We will compute the currents I1 and I2, add them using Kirchhoff's current law to find Is, determine the voltage across the line impedance, and finally use Kirchhoff's voltage law to add the line voltage and load voltage to determine the source voltage. The magnitude of current I1 is equal to P1 divided by the magnitude VL times the power factor PF1. All of these values are given. All we need to do is plug them into the equation, and we get 60K divided by 240 times 0.85, or 294.12 amps RMS. And the phase angle may be found from the power factor, which is given by theta, which is equal to minus the inverse cos of 0.85. We are told that the power factor is a lagging power factor, so the current will lag the voltage, hence a negative sign for the angle, which is minus 31.79 degrees. The phasor I1 is 294.12 at minus 31.79 degrees amps RMS. For the current I2, we will go through the same process, starting with the magnitude of the current I2, which is given by P2 divided by the magnitude VL times its power factor, PF2. All of these values are given. All we need to do is plug them into the equation, and we get 40K divided by 240 times 0.78, or 213.68 amps RMS. And the phase angle may be found from the power factor, which is given by 0 equal to minus the inverse of the cosine of 0.78. We are told that the power factor is a lagging power factor, so the current will lag the voltage, hence the negative sign for the angle, negative 38.74 degrees. Again, the negative sign is the result of the fact that the power factor is lagging. Thus, the phasor I2 is equal to 213.68 at minus 38.74 degrees amps RMS. Using Kirchhoff's current law, Is is given by the equation I1 plus I2. Plugging in the actual values, 294.12 at minus 31.79 degrees, plus 213.68 at minus 38.74 degrees. Converting to rectangular coordinates in order to carry out the addition of these feeders, 250 minus J154.9 plus 166.7 minus J133.7, and adding them gives us 416.7 minus J288.8. Expressing this in polar coordinates, it equals 504.1 at minus 34.25 degree amps RMS. Then Kirchhoff's voltage law tells us that the source voltage, Vs, is equal to the voltage across the loads plus the voltage drop across the transmission line, which provides us with this equation. Vs is equal to 240 at 0 degrees plus Is times 0.1 plus J 0.5. We know the value of Is, so we can plug that into the equation. And that equals 504.1 at minus 34.25 degrees times 0.51 at 78.7 degrees plus 240 at 0 degrees. Multiplying these two polar coordinate phasors gives us 257.04 at 44.44 degrees plus 240 at 0 degrees. And I won't bore you with the step of converting the polar to rectangular coordinates and back again. The final answer is 460.17 at 23.02 degree volts RMS. Or in nice round terms, it's 460 volts at 23 degrees. And that does it for this problem. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. When it comes to residential power backup, 𝐃𝐈𝐒𝐂 offers a range of solutions suitable for everything from powering a single appliance during a short outage to running an entire home in the event of an extended blackout. You can have a look at all of these options that are available by simply going to this web address. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.